know you will be quite tired after a whole day talk. I'll try to be very quick. So, hello everyone. It's my pleasure to be here to share our recent work. And these two, I'll talk about two work. These two recent work were done mostly under the guidance of Tommaso Trio and Xianlong, and we present our recent measurement of gas-phase metallicity of mass metallicity relation and fundamental metallicity relation for dwarf galaxy and cosmic moon. The mass metallicity relation is an observation findings that describing the statistic nature of galaxies, which plots the stellar mass and gas phase metallicity. And this most famous result provided by Trimotti use 53,000 SDS galaxy at the local universe. And it has been widely included into the textbook. It's important to note that this positive correlation is not so obvious between an absolute value of stellar mass and a relative value of gas phase metallicity. And that is to say, if we made a crude assumption that if galaxies are grown and piled up with only mass grown, that the metallicity should be should be flat. Obviously, it is not the case in the real world. So the mental production and the mental production and the mental consumption for low mass galaxy may be quite it's very different from that of the high mass galaxies. So this suggests that the galaxy this suggests that the process that govern the metallicity may be very different. So the observation and simulations of MZR will therefore help us to explain this difference and help us to understand galaxy evolution. And as you know, at high redshift, the galaxies experience very violent star formation activity. And for dwarf galaxies, the potential value is very low. So that's why we want to extend. And let me briefly introduce the galaxy evolution model. As you know, for mantle, there are two sources, that is stellar production and inflows, and two destinations. Locked in the long-lived star and outflow, and the rest in the reservoir is the gas phase metallicity that we care about. After the derivation of formula, the most important term affecting the MZR are the mantle loading factor of outflows and the gas fraction. So let's move to our results. Here are the examples of our reduced 2D and 1D spectrum using forward modeling technique from our class JWST NIRISS data. We marked several emission lines that we will use to estimate the metallicity. In addition to the increased power of JWST, the magnification of gravitational lensing will also play an important role in helping us extend the MZR. Here are the magnification maps based on our latest lensing model and the position of our galaxy sample. We have selected 15 galaxies in this lens field. And finally, we selected the 1D spectrum according to their redshift and stellar mass in order to obtain high signal-to-noise ratio for metallicity measurement. We must acknowledge that our sample of just 50 galaxies is still not quite abundant for statistics study, and with only 10 galaxies per subgroup. That's why we are doing next to find more samples. However, here is our MZR measurement Here's our MZR measurements from glass data. Their metallicities are inferred from line flux ratio calibration using our Bayesian method, and their stellar mass are measured using SED fitting from our photometry catalog. And our result reveals that the MZR is still present in a low mass end and match well with that in the literature. And I will explain more later. As we acknowledge, the 15 Galaxy from previous work is still not sufficient enough for statistics analysis. So we have to try to find more usable data. And the NG Deep survey is one of the most deepest NIRISS observation currently publicly available, with their exposure time eight times deeper than glass. And it is expected to observe more than 500 dwarf galaxies, and will allow us to greatly expand our knowledge at cosmic noon. All the results below are preliminary, and this work is about to submit. So using a similar method, we find 3 times more sample than the glass field, and expanded the MZR to even lower mass. The MZR from the NG Deep show pretty good agreement with our previous work from glass. So for the first step, this agreement confirms that the MZR relation is robustly maintained in high redshift of galaxies, and our slope is very consistent with their high mass counterpart at cosmic noon. So this consistency of nearly 4 orders of magnitude across stellar mass suggests that the similarity and the priority of the progress, which determine the slope of the MZR throughout the whole galaxy formation and evolution model. This result will provide a crucial constraint of the MZR to serve as the benchmark for future observation and simulation. And let's go back to the very beginning. How can we use this measured metallicity and MZR to understand the galaxy evolution model? We followed the standards model and the gas fraction provided by Taconi. We can calculate the mental loading factor of outflows and compare it with the gas fraction. Thanks to expansion of the sample, we clearly find that the dominant component changed significantly at around 10 to the 8th stellar mass. That is, the gas fraction, other than the loading factor of outflows, will gain more weight and even become dominant at the dominant metallicity for dwarf galaxies. And finally, we use this extended data to test the existence of the fundamental metallicity relation. The FMR describes the secondary negative correlation between metallicity and star formation rates. We divide the sample of redshift 2 into low and high star formation rates, and then do stack according to their stellar mass. We do clearly see this negative correlation. That is, metallicity of the low star formation stack shows high metallicity than high star formation stack. So for the first time at this redshift and mass range, this strong evidence guides us to fit the MLR proposed in the local universe, and the FMR we obtained from our field are quite consistent with the result in the literature, providing that the high redshift of galaxies have similar mental abundant history with their low mass with low redshift and normal galaxies. And so here's the summary.
Questions?
How do you actually measure your metallicities? Could you say something about that?
We measured our metallicity using line flux ratio calibration. That is strong line calibration. That is we could calibrate our metallicity from two-line ratio. For example, the O3 H beta from O3 H beta ratio or O3 and O2 ratio. Yes, that is strong calibration method. Yeah, we have to involve oxygen, and we have another diagnose that we can contain. And we could also use the sulfur 2 and L alpha ratio to determine the abundance of metallicity. But the oxygen is the main part.
Okay, question.
Yeah, really great talk, thank you. I'm always curious for FMR analysis, which star formation rate tracer was used here? Was it H alpha or UV continuum?
You mean the star formation rate tracer? Yes.
Yeah.
We use the H beta based star formation.
Awesome. Okay, thank you.
Okay, more questions? Okay, so let's thank to the speakers of this session.